CS 1010X Lecture 11, Generic Operators.
Okay, so this is the agenda for today. Before we start, let's have a recap on the complex arithmetic package that we saw in the last lecture. So in this lesson, we are dealing with what we call imaginary numbers. Okay, so the numbers of the form x plus yi, where I is an imaginary number, and this is equivalent to square root of -1, right? And there are two different forms for these imaginary numbers. There is the rectangular form of this nature, whereby it's x plus yi, and there's also the polar form, which is of the form r times e to the power of ia, where r is what we call the magnitude, okay, or this is the length, right, of this imaginary number, and a is the angle, right, over here. Well, for this topic, you don't actually have to understand imaginary numbers so much. You just need to know some definitions. Let's continue. So let's take a look at this. So the problem here is that you have two different representations of these imaginary numbers. One is a rectangular representation. Okay, so this is the x plus yi version. And the other one is the polar representation, which is the r times I theta. And your job in this problem is to build this so-called complex arithmetic package. Okay, what happens here is that once you build this package, then we can build these four operations: to add, subtract, multiply, and divide. Okay, over this particular package here. This complex arithmetic package over here will basically be the interface between these four operations and also the underlying representations, right? So that's the general idea. So now let's see. So what we want to do is to do something that's similar to the rational number package in lecture 7, right? And there's some basic operations for complex numbers. So let's say z or z is the complex number. You add two z1 and z2 together, right? Then the real part is just the sum of the real parts, right? And the imaginary part is again the sum of the imaginary parts. This is nothing special. It's just the definition, right? And similarly, if the rules that you can apply, and for example, multiplication, if z1 times z2, okay, essentially you have you can get it by multiplying the magnitude, okay, and by adding the angle. So you don't have to understand why it's like that. You just know that there's some rules, right? And you can Google and check out all the rules for complex numbers, multiplication, subtraction, addition, and division. What we do is that we can assume that these four functions exist: real part, imaginary part, magnitude, and angle, right? And then if you can make complex numbers from real, imaginary parts, or from magnitude, angle, then we are done. This is exactly analogous to essentially the rational number package. Right, so this is the code for the rectangular coordinates, right? And so the idea here is that you make from real imaginary, so x is the real part, right? And y is the imaginary part. So when you do this, you return a new tuple, xy, to represent the imaginary number, right? And obviously, the real part is x, and the imaginary part is y. Okay, so it's all good, right? And use hypotenuse, okay, to compute their magnitude. So this is just square root of x squared, right, plus y squared. This is this definition, right? And angle is the arctangent, okay, of y over x. So this is just the angle, right? Because if you have this rectangle, right, and this is y, this is x, then this is the tangent, arctangent. If you want to make the imaginary number from magnitude and angle, right, you just have to know that x is r cos theta and y is r sin theta. So let's take a look at the code. Okay, now suppose we have a new function called print complex. Okay, and essentially what you do is you convert the real part into a string, and then you convert the imaginary part into a string, and then you just add a plus here. So for example, if A is make real imaginary 1, 1, and B is make real imaginary 2, 2, right? Then if you print A, print B, you have 1 plus 1 I and 2 plus 2 I. Now, suppose you do add complex, as we explained earlier. Add complex, you just make from real imaginary. You add the real parts together, okay, for the new real, and you add the imaginary parts together for the new imaginary part. And then now what you can do is you can print complex, right? Print complex of add complex A and B. Answer will be 3 plus 3i. Good. Now let's look at the other polar coordinate version. So what happens here is that instead of storing x and y, we will store r and a. So this is the magnitude and this is the angle. Right. So again, you store it as a tuple. Okay. And because of that now, so the magnitude is the first one, right? And the angle is the second part, right? And this time to compute the real part, you use r cos theta. Imaginary part is r sin theta. This is the math, right? And then if you want to make this representation from real imaginary x and y, essentially you compute the magnitude and compute the angle, and then basically you store these two. Okay. Now, so let's look at the code again. So suppose now U2A is made from real imaginary 1, 1 and make from real imaginary 2, 2 as B. So this is exactly the same as before. Now, if you print A, you get this. Okay, you print B, you get this. And if you do add, okay, this is the same code from before, right? And then you get this. Right, so it's exactly the same, except now you have this imprecision because you're storing, instead of storing the real part and imaginary part, you're storing the magnitude and the angle, and then because there's finite precision, so there's some imprecision errors that will propagate back when you compute the x and y. Okay, 2 lessons that you need to learn from this example. Number 1, different representations might have slightly different accuracy because of the internal representation. So you see that the polar version of this representation actually gives you this errors. It means you don't store the x and y, you actually store the magnitude and angle. So that causes you to have some errors when you show it. And the other thing is that you notice here that we define 2 different representations, right? But the code for print complex and the code for add complex, they are the same code, right? So both of them you just write, and then the representation actually was changed between the 2 forms, and essentially the same code could run. So this is an illustration of the power, right, of data abstraction. Okay, right now hopefully you have all started appreciating this abstraction. Right, and now we come to the main problem for today. The problem that you need to look at is the following, whereby there are many coexisting representations for the same data object. The goal here today is for you to appreciate what the issues are and also learn about some techniques that we can use to deal with this problem. So let's recap. So we just saw the complex number package, right? So what happens here in this world is that there are 2 different representations for complex numbers. There's a rectangular version where it's x plus yi, and there's a polar version where it's e to the I theta, right? E is where it's magnitude times e to the I theta. So there's a magnitude and there's actually an angle. Now, so what happens in this world is that there are many data objects. Okay, they're all rectangular, they're all complex numbers here. Okay, but there are some which are in rectangular form. That means they are x plus yi. You're storing the x and the y. And then there's also those in polar form where you store r and theta. Now, it turns out that when you look inside them, they look the same because why? They're all tuples. So both of them are tuples, and unfortunately they are different, right? Because they are representing the numbers in a different way. The basic problem here is the following, right? You have the same operations, okay, for both the polar and the rectangular form. Our challenge really is to make sure that we match the functions for the rectangular version to the rectangular representations, right? And we match the polar versions to the polar forms, right? So how do you do that? Okay, so one challenge of having multiple representations within the system is that we need to be able to match the representations to the right operations, okay? So the rectangular representation must be given to the rectangular functions, okay? And the polar representations cannot be given to the rectangular functions or vice versa, otherwise things blow up. Okay, the second problem is that the name conflicts, right? So if you look at the functions for the 2 forms, the polar as well as the rectangle, you notice that the functions are called the same. I know they're called real part, and angle and so forth. But it makes sense, right? Because they are pretty much doing the same thing, except that they're working on different data representations. Okay, so first let's take a look at how we can match the representation to the operations. Okay, first of all, it's important to make sure we know what is the data type. So for example, in the complex number example, we just thought them as tuples, right? So both the rectangular form and the polar form are just tuples, and it's hard to tell them apart. So one simple way is to make sure that we indicate a type of the data type inside the representation. So for example, we tag the data with some tag. Alright, so this is a simple way to do it. Essentially, we can have this function called attach tag. Alright, it takes a type tag and then some contents. Okay, and essentially what you do is that you will add this tag to the contents. Right, and another thing you can do is, for example, is that we can extract out the tag. Right, so type tag of datum is the data object. Right, and then you check that the datum is a tuple, because if not, then you know it's not data object, and the length is 3, and you return datum 0, because you know that datum 0 will be the type tag. Okay, and there's this thing here called exceptions, whereby you raise the exception. So what it does is that it complains that something bad has gone wrong, and this is when you see error messages. So let's take a look. And you also need to be able to extract the data, right? So basically, the contents is used to extract the data from the datum or data object, right? If again this is true, it's a tuple, and the length is 3, we will extract out the rest. Okay, so datum 0, remember, is the tag. Okay, again, if it's bad, then we just complain. Now, so let's take a look. We can do a very simple thing, and for example, instead of just using the old version, you actually modify Ben's constructor from the original xy to this thing where you attach a tag called rectangular, alright, to xy. So this ensures that the data actually has a tag, right? And similarly, you also update the lister's code, right, the polar one, to add a polar tag. Okay, so this is what you do. Now, and basically to check that the data is the right type, you can use you can create a new kind of a type checking function. For example, it was rectangular. Okay, it's Z or Z, right? We'll check that the type tag of Z is rectangular. Similarly, you can have a similar polar version, right? Okay, so this solves part of the problem, but there's still a problem, right? Because Ben's and Lisa's functions still have the same name, so there's naming conflicts. So we have to figure out how to deal with this, otherwise it's not going to work, right? Now, so this also actually has a simple solution now, which you can is that you can impose a naming convention. That means a function name should end with a tag, right? So originally it was make from real imaginary, right? Now we make from real imaginary rectangular. So we know that this particular function returns a rectangular type representation. Similarly, if you do make from real imaginary polar, this will do a polar version. Okay, so have we solved the problem? So basically what we're saying is that you need to ensure that every data type has a tag, right? So you look at the data type, you know what type it is, and then you basically rename all the functions appropriately so that you can ensure that you know which function you're dealing with. There's no naming conflicts, and then all you need to do is look at the data type, and then you basically find the right function and you just match them. Well, this sort of solves the problem for some cases, but let's just pause to ask ourselves a question. So whose responsibility is it to match the data type to the corresponding operations, right? Is it the users, Ben's, Alyssa's, or is it someone else's responsibility? All right, now let's take a look what happens if we make it the user's problem, right? So that means we make it the user's responsibility to ensure that the underlying data representation matches the correct version of the function that is needed to do the work. So what happens? Well, let's take a look at what happens to the function at complex. So what we need to do now is to check whether the content of Z1 and Z2, whether they are polar or rectangular. So first we do this real 1 equals to real part polar of this thing, okay, contents, and then we do this thing. Now, basically if Z1 or Z1 is actually rectangular, then okay, we did it wrong here. Okay, so we will redo it. Okay. Similarly, we extract the real and imaginary parts of 2 of the second number using the same method. Okay, so once we have done these 2 steps, right, then we know that real 1, imaginary 1 is, so real 1, imaginary 1, that means this is the real and imaginary parts of Z1, right, and real 2 and imaginary 2, they are the real imaginary parts of Z2, right. So what we do then is that we just add them up over here. Okay. Now, what we notice obviously in this implementation is that there's a lot of code. There's like 8 lines, right? That's used, well, more than that, 10 lines. 10 lines are used to just check whether or not what is the type, and then to extract the right thing. Okay, so similarly, if you look at the rectangular code, okay, for the real imaginary, essentially what happens here is that if you make from real imaginary rectangular, you attach the rectangular tag. Okay, everything else is similar to before. Alyssa has the same kind of code, right? So you add another polar tag here. Everything else is similar to before. Okay, so with this, we have actually succeeded in taking care of this multiple representations. So the key idea here is that you tag the data type, and then you have a check to see what is the data type before you do the things with it. Now, this is fine and dandy if you want to do it once. The problem is that something else may happen in the future, right? So parent's code can be removed because somehow you decided it's no good, and then you have only Alyssa's code left, right? And then after that, you may also have a situation whereby you need a new representation for complex numbers, and so you have a third representation of complex numbers. Okay, or maybe Alyssa decides that she wants to provide a new function for polar representation that no one else can provide. Okay, so now, okay, what should we do, and who should be responsible to make the above changes so that everything works? Now is where we come to the meat of this lecture. Then this is the kind of the crux of this class. We're here to teach you how to apply different techniques, right, to manage the complexity.